Welcome to The Explainer. Today, we are going to get into the physics of everything that wiggles, vibrates, and swings. We're going to crack the code, the elegant physics behind what we call oscillation. You know, from the gentle swing of a pendulum clock to the vibrating string on a guitar, there's a fundamental mathematical language that describes all of this motion. So, what is this hidden code? What governs everything that oscillates? Well, the answer is a concept called simple harmonic motion, or SHM for short. Now, this isn't just any random back and forth movement. Oh no. SHM is the purest form of this. It's like the ideal rhythm, where an object's position over time can be described perfectly by a smooth sine or cosine wave. It's the gold standard of wiggles. And here it is. This is the code itself. This is our master equation. Now, I know what you're thinking, but don't let the symbols intimidate you. Seriously, don't think of this as a problem you have to solve. Think of it more like a control panel. It's got three simple dials, A, omega, and phi. And these dials let us describe and predict literally any simple harmonic motion in the entire universe. Okay, so let's play with this control panel. We're going to start with our first dial, the amplitude. This one is all about the size of the motion. The amplitude, which we represent with a capital A, is actually super simple. It's just how far the object moves away from its resting point, its center. You just measure from the dead center to the absolute farthest point of the swing, and that's it. That's your amplitude. It's the peak of the wave. And you can see it perfectly here. On the left, a low amplitude gives us this small, kind of gentle motion. But on the right, you crank up the amplitude and you get a big, wide, energetic swing. And get this, both of them could be happening at the exact same speed, but the size of the motion is totally different. That's the power of just our first dial. All right, let's move on to our next dial, angular frequency. This is how we're going to build up our understanding of the motion. This dial, it controls the speed of the wiggle. So, angular frequency. It's that Greek letter omega, and it tells us how quickly the oscillation is happening. The most important thing to get is its relationship to the period, t, which is just the time it takes to do one full back and forth cycle. So if you have a big omega, you get a small t. That means a faster, more frequent oscillation. And if you have a small omega, you get a big t, a slower, kind of lazier motion. And you can really see that effect right here. Now, look closely. Both of these motions have the exact same size, the same amplitude, but they feel completely different, don't they? The low-frequency one on the left is slow, methodical. The high-frequency one on the right is rapid, frantic, full of energy. And all we did was adjust that second dial. Okay, time for our third and final dial. Now, this one can feel a bit more abstract, but I promise you it's actually really simple. The phase constant is all about the starting position. Think of it as the head start. Think of it this way. Imagine you've got a stopwatch. The phase constant, that Greek letter phi, describes exactly where the object is in its cycle at the very instant you press start. Is it at the far end? Is it right in the middle? Is it somewhere in between? That's all the phase tells us. It just locks in the starting conditions. So here's the simplest case. When the phase is 0, it just means our observation, our stopwatch, starts at the exact moment the object hits its farthest point, its maximum amplitude. But what if we started our stopwatch when the object was zipping right through the center? Well, as you can see here, that's no problem. We just change the value of our phase constant, and the equation can perfectly describe that different starting point. The phase gives us the power to start our description from any point in the cycle. It's incredibly flexible. So, let's put it all back together now. We've seen how these three simple dials, amplitude, frequency, and phase, come together in our master equation. And what they create is a complete blueprint for any simple harmonic motion you can think of. And this is the real key takeaway. These three numbers, A, omega, and phi, are completely independent of each other. You can change the size, you can change the speed, or you can change the starting point. And together, they give you total control to describe any oscillation. And this is the true power of this equation. With just those three numbers, you don't just get some vague description of the motion. You get a precise prediction. You can calculate the exact position and velocity of that object at any moment in time, past, present, or future. Its entire path is mapped out. It's incredible. And that wraps up our look at the elegant code of simple harmonic motion. It really makes you wonder, doesn't it? If one simple, beautiful equation can so perfectly describe the rhythm of a pendulum, What other mathematical codes are out there just waiting to be discovered? Codes that describe the much more complex, messy, and beautiful rhythms of our entire universe.